I'm Dan Sweeney from MathSpec Incorporated. In this video, I'll demonstrate how our Excel add-in can help identify an unknown compound from its accurate mass fragmentation data. This unknown compound is a derivative of atrazine. The data used in this demo is not from an authentic sample or an isolated metabolite, but you will see later that my proposed structure based on our rational numbers Excel add-in is probably correct. Carolyn Huber and her co-authors recently developed a novel high-throughput workflow for screening pesticides for human metabolites. The objective of their work was to develop a very useful workflow, not to perform structural elucidations of the numerous metabolites that were generated in their study. They have shared with MassBank many of the high-quality accurate mass MSMS data sets that were produced in their study. In this video, I will analyze the fragmentation data of one metabolite of the herbicide atrazine, MassBank HB 002826. Huber et al. Had already determined that this metabolite, which they called atrazine decimin, had the molecular formula C8H13Cl N4O2. Our objective here is to determine a tentative structure for this derivative of atrazine. I've cut and pasted the mass intensity data from MassBank into a Microsoft WordPad document. I've imported the fragmentation data from the WordPad document into a new Excel workbook, sheet 1. So the masses are in column A and intensity in B. Now I could check the formula. You make this a little bit bigger. So this is going to equal the mass of the precursor minus the mass of a proton and then minus the mass of the atrazine in C24. So it's 16.9786. Now we could do the mass of an O2 minus the mass of NH. Okay, and it's almost identical. So this formula does indeed look really good for the unknown metabolite. So now the next step is to open up the worksheets that we need. So I'm going to click on add-ins. So let me expand that out to the video area. So the data input worksheet has some blue areas where we need to import some data. I'm going to go back to sheet 1. Okay, and I also need the isotope pattern of the precursor, and that data, the full scan data, is not available. I will go and use the formula for atrazine as an approximation. So we can calculate this. And we also need to have the precursor ion in the set of data that we're analyzing. In this case, the compound, the precursor did not survive the fragmentation energy that was used. So again, it's not really a big problem because we can copy the precursor mass. Okay, and this should be 2%. The largest, most intense ion is about 500,000. So 5,000 would be 1%. So I'm going to make this 10,000. This will not affect the scoring. Whoop, it's bigger than I need it to be. This will not affect the scoring at all. And there's some parameters for this. Is positive ion data, for example. I'm just going to use the default parameters, which excludes fluorine and has a 3 millidalton air window for mass and 9% for the isotopes. So we should be okay here. And now I'm going to click on the transform to start the analysis. Some of these fragment ions could be viewed as being composed of smaller subfragments, if you will. And there are, we'd like to know the masses of these possible subfragments. So we can use neutralized fragment ions, simple differences between fragment ions or between a precursor ion and fragment ions, and some mass differences. Those are basically the three types of possible subfragment masses. Now we look at the computer can go through and check for sets of masses that sum up to the mass of the precursor molecule. These are the subfragment masses, and this operation is very CPU intensive. The subfragment masses are then converted into subformulas. Because mass to formula is usually a one-to-many relationship, often multiple molecular formulas for the whole molecule are possible. The last thing the Excel add-in does is it checks to try to assign the subfragments in space, and that's based on using logic tables. So the transform is complete, and now we have modular structures and partitions. If I move this over, go back to data input. So this particular run took 13 seconds. So I'll go back to partition 1, and the score, the highest score would be partition 1, and the lowest would be partition 6. The partition score is based on how many fragment ions. In this case, we had 7 fragment ions that can be explained by these 4 numbers here, these subfragment masses. Now, in addition to how many, we also look at the intensities, or relative intensities. The next thing we can look at, so the upper part shows that with this particular alignment, this was linear. This is the arrangement of these subfragments. Now they could be arranged in a different way, still linear. And it also, the size of these pieces up here are directly proportional to the mass. If we go and look at the lower graph, the fragment masses now, the subfragment masses, have been converted into formulas, combinations of atoms. And we did get the same molecular formula that Huber et al. had reported. This is the average mass error of these subfragments from the formulas, from the theoretical mass of the formulas. And it's in millidaltons, so the data is very good as far as matching this particular formula and subformulas. The relative feasibility is how it takes into account both the mass error and how common these fragment formulas are. Now there are two, let's see how many, there's three. Okay, so there are three alignments that are all consistent with the data. I'm going to choose this all connected to white right now, and you'll see later why I'm doing that. So I can view these as this thing, if you will, in the middle, and each of these other three subformulas are connected to that. So I can redraw this as one of the modular structures of the analyte. So this is partition 1. So we basically have four subformulas. Now, the reason I chose that one is I can run the same analysis on MassBank's spectrum LU071803, which is an authentic sample of atrazine, and compare its modular structures to the known structure of atrazine. And what I find is that this particular modular structure, which matches the modular structure for the unknown metabolite, it's very similar, and it also will correlate with the known authentic sample of atrazine. The number of hydrogen atoms in the subfragments will often differ from the number of hydrogen atoms in the corresponding substructure. So now let's compare the modular structure of atrazine, which we chose because it matches the structure of atrazine so well, to the modular structure of our unknown metabolite. There's two changes in the modular structure of the metabolite relative to atrazine. First, there's apparently an extra oxygen on the isopropyl side chain. And second, let's look at this white subfragment. To go from a C2HN3 in atrazine to a C2N2O in the unknown metabolite, one way we could do it is to lose ammonia and gain water, sort of a hydrolysis of the compound. There are three nitrogens in atrazine we could replace, so we could do the one on the right, the middle, or the left side. So I'm going to look at each of these possibilities. Now these two are similar chemistry-wise because each one replaces the nitrogen atom that connects the alkyl side chains to the central ring system with an oxygen atom. So what's the likelihood that this change can be made? It appears that changing this atom should result in loss of the side chain. So basically, this is just a part of the atrazine ring system, and if we hydrolyze that with water, attack here, we're going to generate an amine, amino alcohol, and we're going to lose the side chain. On the other hand, about the only way that I can see that we could keep the side chain on the molecule and change to a oxygen would be to do a cyclization. And so now we do have the oxygen connected to the ring system, but now we have an amine instead of an alcohol out here. So if we then, you could argue that we have an amine and it could go through monoamine oxidase and go to an aldehyde, and the aldehyde could go to an acid, but it's not likely under the conditions that they did their studies that we'd get reduction to an alcohol. So it's very unlikely that the replacement of the nitrogen with an oxygen is done outside the ring system. So replacing the middle nitrogen explains the fragmentation data well for partition 1 and this proposed structure here. Now, two other structures were consistent with the same modular structure, but there was no plausible way that these structures could be formed without cleaving the side chain. Although this structure may make sense and is probably correct, this identification is still tentative. There's always some ambiguity in the interpretation of mass spectral data of unknown compounds. So the mass spectrometry reveals only blocks of atoms. The detailed molecular structures that we see are induced from mass spectral data, but those are all in the mind's eye. We must always assume that the simplest explanation is the most likely explanation of the data. Thank you.